start recording here. Okay, so first up is 6033 in the news, which is today 6033 on Mars. So you all might have seen in the news that Perseverance has landed on Mars, which is super exciting. I am very into space and things that happen in space, as I know a lot of the staff are as well. In fact, last year's design project was sort of about a system in space, and it was awesome. And there are a ton of interesting things that we could say about how 6033 relates to this. I'm just going to call out a few, and then I'm also going to let Christabel say some things about Perseverance, because I know that she's excited about this as well. You can look up the specs for this system. So you can see, for instance, here are the specs on the processor and memory. Here is some information about some of the network connections, because we haven't gotten to networking yet, but that's fine. And what you can see if you read into these is that if you're designing a computer system that exists in space, you have a lot more constraints than you do on Earth. So for instance, the radiation on Mars will destroy the type of memory that exists in our computers. So there's all these interesting hardware things to deal with. But you can also see that the constraints of these devices are really harsh. They're working with very, very little memory, and they're communicating with Earth on a connection that is much different from any of the network connections you're normally dealing with, right? So you can see it takes between 5 and 20 minutes for a signal to get from Mars to Earth. So for like a bit of data to get from Mars to Earth, it can be almost 20 minutes. To give you some context, if I wanted to send a piece of data from here to California, maybe 50 milliseconds, right? So this is much longer. And so you have all of these interesting design constraints about how do you build something that works on this very small machine that can deal with this network that has these really, really long delays and often really, really low throughput. It can't get that much data through. It's just really interesting. Christabel, do you want to say anything about Perseverance and how amazing it is?
Oh yeah, I was really excited when I learned about this, but I thought I should get you students extremely pumped for the course material, because last year's project was precisely about everything that's Perseverance. So they were designing a space network communication called Extranet, Extraterrestrial Network. Ha ha ha, very imaginative. This was great because they had to think about variability in round trip times, intermittent connectivity, very limited resources such as bandwidth and power. And the best part about this project was and for this year as well, I don't know what the project is going to be like, drum rolls, ha ha ha. The best part about this year's project is that you guys get to be part of the 0.00000, yes, 4 zeros, 1 of the world that gets to think about these kinds of problems and optimization. So get really pumped about virtual memory and the class in general.
Christabel, that was very good. That was very good hype for the semester. So yeah, systems are everywhere. Space is so cool. Like, I mean, this thing is on Mars and it talks to us, right? Like it communicates with us. That is so amazing. So yeah, space is really cool. Let's talk about virtual memory, which also exists in space. Okay, so there's going to be a lot of content in this lecture. We're going to talk about how virtual memory works, but the more important thing you should get from this is why we are using it. All right, but let me kind of orient you into this world first. All right, so we've talked, this is really the last 2 times, we've talked about enforced modularity, right? And we've seen how to do that with a client server system, at least at a high level. And then on Monday, we were talking about naming, right? Which is pervasive in systems. It's how modules communicate. We talked about it specifically in the context of DNS. That's a really good case study, but it's everywhere, all right? You're going to see another aspect of naming today. All right, so what we're gonna start today though is, this client server model, it doesn't work everywhere, right? What if you don't want to put each module of your system on a separate machine, right? That's a very, very reasonable thing. You probably don't want like one laptop for email and one laptop for Zoom and one laptop for Spotify and one laptop for Netflix. Okay, that would be a nightmare, right? So we have to figure out how to get all this sort of enforced modularity working on a single machine. And that's what we're going to be doing for the next couple of lectures, right? And so it is the job of your operating system to do this, right? The system that enforces modularity on a single machine is the operating system. So we're going to talk about how operating systems do this. And this is going to get us into a lot of different topics. So just for me to get a sense of the virtual room here, I'm gonna give you all a quick poll. It's totally anonymous. I'm not going to share the results unless I think they'll be useful to all of us. So again, anonymous. I'm going to put some words here in this poll. I want to know which of these words you've heard of, which of these words you feel like you understand. All right, it's totally anonymous. It's totally fine if the answer is none. All right, I'm just trying to get a sense of sort of, where you're coming from. So I'll watch this for a couple of seconds. I'll give it about 10 more seconds. If it's not showing up, or if you haven't been able to answer, don't worry, we're not looking for super precise data or anything like that. All right, so this is excellent. So it turns out many of you have heard at least one of these words, right? Every single word. There's some people in the room who haven't heard the word before. That's totally fine, right? Some of you have never heard virtual memory, you've never heard kernel, never heard memory management unit. That's totally fine. And then I would say by and large, fewer of you feel that you understand these things. And that is fine. This is, I'll be honest, this is what I expected and kind of what I hoped for. So if you're in, if you're in this class and you're feeling like, I saw this big like system stuff and I feel like everybody's coming in with this knowledge and they already understand it, not true. I have the data. Okay, so we're going to try to get you by the end of this lecture to at least know all of these words. I will definitely say all of these words, and hopefully you will understand most of them. I'll give myself the bar of most of them. All right, so let's return to operating systems. What is this operating system going to have to do? All right, enforcing modularity on a single machine. In some ways, we're going to try to replicate what we had going on the client server model. Right, so we're going to focus on three things. We could talk about more things related to operating systems. You can take an entire semester on operating systems. We're going to focus on three things here. One is that we don't want programs to be able to refer to each other's memory. Right, that is kind of the first thing we're going to think about. Right, we don't want them corrupting each other's memory. So that's one thing we have to do. Now, if we have programs that are just entirely separate, that's not a very useful system. And in fact, that's not what we had with the client server model. We had an ability to communicate between these two modules, right? And so we're gonna want that too. Despite this separation of their memory, I want them to be able to communicate somehow. The third thing that we're going to care about is, if I'm running two programs on my laptop, even if they're totally well behaved, they're not trying to access each other's memory, they're not trying to communicate, I would like them to share the processor well. For instance, I don't want, if I'm running Zoom, I don't want Zoom to hog all of the computing power on my machine. I would like to be able to say, also check email, right? And especially if there's a bug in Zoom, right? I'd like to be able to do some things there. So we're eventually going to get all of these things to work. We're going to spend one lecture on each of these. And you will see as we go through this that there is a commonality in how we address all of these things, right? The technique that we're going to use is known as virtualization, right? So word number one, now you have all heard the word virtualization. Right? Virtualization is a technique by which the operating system interposes itself between a program or set of programs and the physical hardware. So it's the job of the operating system to simulate the interface of the hardware to a program, right? In some sense, if we are properly virtualizing this system, we want every program to kind of think that it has access to all of the hardware, when of course it doesn't. And it's the operating system's job to deal with that, right? Now, I think at this stage, virtualization probably seems like kind of an abstract concept. So we're gonna make it concrete today. We're gonna focus on this first challenge, all right? The way to prevent programs from referring to each other's memory, we're going to do through virtual memory. We're going to totally punt on the other two things today. We're going to assume programs do not ever need to talk to each other, and we're going to assume one program per CPU. But over the course of a couple of lectures, we'll get rid of all of these assumptions. So this is what we're going to do for today. So before we get started with virtual memory, let's just talk about your computers. All right, so what is going on here with these devices. All right, I'm going to draw for you. I can even make it bigger. Well, why press or left? We can use this size. All right, so we are going to care about sort of two things right now. I'll move this up so to make sure it's visible as soon as I draw these two things. We have a CPU and we have memory. That's not my best rectangle, but it'll work for now. So we have a CPU and memory. All right, how are they interacting, right? Forget virtual memory, just what is going on here? Well, in memory, we have, instructions for whatever program the CPU is running. We have some data stored in memory. And this CPU has some instruction pointer, right? You'll often see the abbreviation EIP in our slides for extended instruction pointer. You'll also see this diagram more neatly drawn on a slide in a second, right? And so this pointer sort of going into the, wherever the next instruction is, right? And it just keeps executing instructions one by one. It might jump around if it's getting commands that tell it to change the control flow. This is the basic setup, right? Before we go any further, I am talking memory here. I am not talking about storage. So memory is like RAM, right? It is small, it is fast, it is volatile. Right? That means if you turn off your machine, anything that's stored in memory goes away, right? Contrast that to disk storage. Disk storage is big, it's slow, it's non-volatile. Something that you save to disk persists, right? So we are dealing with memory today. So again, this CPU, it's loading and running instructions, all right? Now, our goal here was to think about this system in a world where we have more than one module or more than one program, right? So let's branch out, right? EIP stands for extended instruction pointer. So I'm gonna have CPU 2 here. Remember right now, we've got one program per CPU, all right? So I've got two processors. It's got its own instruction pointer, all right? It's got its own instructions, its own data, right? It's doing its thing, right? But now you're in the world of modularity. This setup is problematic. There's nothing here preventing, say, CPU 2 from just going in to CPU 1's instructions, data, and messing up with everything. There is nothing enforcing modularity in this picture that I've drawn for you. So let's progress. All right, let's try to do this. So, we want the operating system to somehow be involved here. So here's my first idea for you, which is going to get us started, but it's not going to work. Kind of like when we were talking about DNS. So one idea is to say, okay, we have in memory. I'm going to draw a line. All right, so CPU 1's instructions and data live up here. They go from, let's say, this is address all Fs, and this will be address that starts with E. These are in hex, right? And then CPU 2's instructions and data live below here, right? And so we can say, okay, CPU 2, you're only allowed to access addresses that live below here. And maybe the way we'll enforce this is we'll include a special piece of hardware, which I'm going to draw as a yellow box, a little bit orange to you. It's yellow in my house. All right, so now all of these accesses go through this piece of hardware, and it checks that each CPU is sort of, abiding by its constraints. Right? Now, we could probably get this to work. Okay, this is not a totally infeasible idea, but it has some drawbacks. What is this? That these programs now have to be written really carefully. Programming on CPU 1 has to be written to only, to avoid a whole range of addresses and things like that. And we've also sort of said, like, okay, well, what if the operating system needed to change the size of these little chunks in memory, or add another program into it, or just rearrange things? This would all start to get very complicated, right? You'd have to the operating system would have to communicate that back to the CPUs, and they'd have to figure out a way to deal with this. Right? It's a lot of complexity for sort of every piece of this picture. And all of these problems, they're stemming from the fact that this is not virtualization, right? In this setup that I have for you here, these two CPUs, they do not think that they have access to the full 32-bit address space. We're going to use 32-bit address spaces in lecture slides because I only have so much space on the slides. So they have to be written to avoid things. This is very inelegant. It is not a good abstraction. It is not going to get us where we want to go. All right. So we're going to fix this. All right. We're going to make this better. All right. So what we want every program to be able to access a full 32-bit address space. We don't want programs to have to be written to avoid particular addresses. But of course, like you and I know that's not happening, right? Programs do not actually have access to all of memory, right? So how will this work? We're going to do this by adding a level of indirection with naming, all right? So that picture that you just saw me draw, we're going to get nicer here, better rectangles, all right? So we have CPU 1. It's got its extended instruction pointer here. We're also going to have CPU 2. I'm not drawing an instruction pointer in it because all of my examples are going to work with CPU 1. I just want you to remember that there are multiple CPUs in the mix here, right? We've got memory over here on the right, 32 bits. It's going to be nice for us to have just some actual addresses to work with. The details of those don't matter in particular, all right? We're going to keep, in this starting example, we can imagine that indeed our instructions and data for program 1 sort of live in their own little chunk of memory. And for program 2, they live in their own chunk of memory, right? But we don't want the two CPUs to have to worry about that, right? We don't want them to have to know about that mapping or think about it in any way. That yellow rectangle that I introduced to you before, oh, there's going to be other stuff potentially, also lives here and now it gets a name, all right? This is another word that I gave you in the poll, the memory management unit, all right, or MMU. So this special piece of hardware is going to sit between the CPUs and main memory, all right? And so let's think about what this MMU's job is, all right? The way this is going to work, and again, I'm going to give you one approach that is not what we're going to end up with, all right? We're going to start, CPU 1 references some address, right? We will start calling this a virtual address. Any access has to go through the MMU, right? So this virtual address gets sent to the MMU, and it's the MMU's job to figure out, okay, well, what physical address should I map this to, right? The MMU is going to keep track of a mapping between the virtual addresses for each CPU and the correct physical addresses, right? This is its lookup algorithm in the context of naming, right? So, okay, to get this to work, one way to do that lookup, a very common and very good starting point usually for just different naming schemes is just have some sort of table, have some sort of lookup table that lets us do this. All right, so we'll have a notion of, okay, there's some table for program 1. You're going to see these in use, so don't worry if you don't feel like you understand the tables quite yet. Some table for program 1, some table for program 2, and it's in this table we get a mapping between virtual addresses and physical addresses. All right, so let's zoom in on what program 1's table might look like. I picked addresses at random, but you can see they are all in the part of memory that belongs to program 1. So this memory management unit needs to take that virtual address and figure out which physical address is right. So let's make an attempt, right? Let's make an attempt with sort of just the most basic idea of how a table lookup might work, or it might look in hardware. All right, so attempt number 1, just use this virtual address as an index into the table. Okay, so this would be a very big number, right? This is in hex, so 2148 in hex. That's my index. I go to that element in the table, and it returns my physical address to me. That is just a table lookup, right? Like go to row 2148 in hex, get it, use that. All right. This is going to fail us. It's not going to fail us because of the idea. It's going to fail us because of the physical realization of this technique. If I tried to do that, that would say to me, okay, for every possible virtual address that this CPU is potentially using, there's going to be a row in that table. All right, well, Addresses are 32 bits. That's 2 to the 32 rows. Each of those maps to a 32-bit physical address, right? So each entry here, oh, I have a pen. I charged the pen so I could do this, right? Like each one of these, maybe I can't do it. Each one of these rows is 32 bits. This table would be 16 gigs. We can't. We don't have anywhere to put that table in memory. All right, so it's a good starting place. This won't work. All right. The solution to this is something that some of you have heard and some of you understand. All right. The solution to this is use what is known as page tables. All right. So let's talk briefly about how a page table works, but more importantly, I want you to understand why we're dealing with them. All right. And part of why we're dealing with them is to solve this issue. All right. So I will start calling these tables page tables. Right. I totally skipped over one problem that we had before. I intentionally skipped over it. These lectures are very well planned, which is, first of all, just how does the MMU know where the table is, right? It needs to read this table, right? So we're going to do that. These tables live in memory. They have addresses. The MMU has page table registers. That's what PTR stands for, that point to these things. So notice that this MMU has a physical address to point to the correct page tables. This is analogous to when we talked about DNS on Monday, and we said, okay, your DNS clients, like your laptops, they need to hard code the IP addresses of the root servers, right? You need some way to bootstrap this system, some way to get it started. These page table registers, that's how we get it started. All right, so how does this page table work? And, like, why have I cut off the addresses? What's going on here? It kind of looks the same as before. All right, here's how this works. So our memory management unit is going to take this virtual address. It's going to look at the top 20 bits. I'm using 20 bits in this example. That is pretty common for these sorts of systems, but it could be different. It doesn't have to be 20. All right, look at the top 20 bits. That is the index into my table. All right, so here the top 20 bits are 2. So you can see I'm going to the second entry in the table if we are indexing by 0, right? So entry 0, 1, 2. All right, that 2 I'll talk about as my virtual page number. All right, so top 20 bits, virtual page number, that's my index into the table. All right, whatever I find at that index, that is the physical page number. That is the physical address of the page in memory that we're supposed to be getting to. All right, so a page here will be equal to 2 to the 12 bytes. You can see the math for that in the bottom corner. All right, so the MMU is going to say, all right, I took these top 20 bits, I mapped it to this physical page number. There are some bits left over in the address. These are known as the offset. All right, and then the MMU is just going to swap the virtual page number for the physical page number, keep the offset. That's the address. All right, if you want to think about this, it's totally possible that even if you've heard of page tables, even if you've thought of them before, the word page might seem weird here. Imagine if we had a book like, oh, I have a book. I have a textbook. Okay, it looks like this. You might have seen it. I could talk to you about a particular word in the textbook, and I could say it was like the 1,000,001st word, right? I could say it that way. Or I could say it's like word 7 on page 60. Right? This gives you a different way to refer to different pieces of memory. All right. So why is this good? Right? This, if I were you, and when I was me in college, this seemed extraordinarily complicated. Like I hated page tables. I really hated this for a long time. But let me tell you one good thing. All right. This table is now much smaller to store. We're only taking the top 20 bits as an index. That means there can only be 2 to the 20th entries. There's still going to be 32 bits. I'll talk about that in a second, because from this slide, it looks like they would only need to be 20 bits. This is much smaller. All right. So it's much, much smaller than what we had before. Right. This is good. Okay. Now, this is the basics, just sort of how page tables work. We can think about this in the context of naming as well. Virtual addresses are the names. physical addresses are the values. The MMU is doing a lookup here via this fancy table, right? It's cleverly constructed table. The context for this lookup is the page table register, right? The one that's pointing to the current table. And you can see that we get a couple things. We get hiding. A program can't access physical memory that's not in its page table. It can't name it, right? We get indirection. I laid this out for you in memory in a nice way so that you could see instructions of data for program 1, instructions of data for program 2, etc. The operating system, though, can move all sorts of stuff around in memory. It can add, new programs. It can fragment things if it wants to. It has to keep those page tables updated, but it doesn't have to be communicating back to the CPUs. It's free to do all of that management on its own and keep this clean abstraction to the programs, right? That is really nice, right? So this is the basics of virtual memory. Now, we are not done. It's 2:32, right? We have two kind of directions to go in from here. And one is addresses a little bit of what's in the chat, right? Here's where we need to go. One, does it really work? Does this actually protect programs from accessing each other's memory, right? We're gonna need to address some other issues first to get there, but that's one thing we wanna do from here. And then we also wanna talk about performance issues, all right? I told you in the very first lecture that performance, kind of pervades everything that we do in this class, even in something that seems as, I guess let's say small as virtual memory. Like it's on one machine, it's one piece of this. There are a lot of performance issues to care about. So we're gonna get into both of these, right? I'm gonna start with the first, but before I really answer this question for you, right? Let me just give you a lingering problem that some of you might have noticed, right? You can look at this diagram. You can say, okay, I kind of understand. I see there's instructions and data for program 1 and for program 2, and there's some space, so I can understand how programs might get added. I can understand what might happen if program 2 finishes. We can free up its memory, put something else there. But what if you just don't have enough memory, right? What if I don't want to run a bunch of programs? Memory is small. What if I can't store all the instructions and data, right? Although this isn't really a question about how do we get virtual memory to work, but this is a place where we can answer it. All right, so how does this work? To answer this, we only really need to care about the page tables, so we can get rid of anything else. And we're gonna do a deep dive into the page table entries. This lecture is just it's rectangles on rectangles on rectangles. It's like the inception of rectangles, all right? Page table entries contain some additional bits that are gonna help us deal with this problem. They're going to help us deal with some other problems, and they're going to bring us back to the answer of, does this really work? All right, so here's what a page table entry might look like. What I've drawn here, top 20 bits, that's where we store the physical page number. You saw that before. These need to keep a 20-bit physical page number, but that leaves 12 bits left over, right? Those 12 bits do some other stuff for us, all right? Here's what one of the bits does for us. We're not going to talk about all of them. We're going to talk about 3. Right, there'll be a bit for each page table entry that just says, is the page currently in memory? Right? Because what your operating system actually does is, it stores things in memory when it can, but if it's running out of space, it will start to push things off into disk, right? To this other big reserve of storage that is, much slower, but much bigger, right? And so if we find that a particular memory address is not in memory, get an exception. It's known as a page fault, right? You might have heard the word page fault, and the operating system goes ahead and handles that. Right. So this functionality allows the operating system to, in a relatively clean way, not even just keep things only in memory, right? Push things off to storage. So because this is so important and exciting, we're gonna take a brief interlude. Okay, interlude away from page tables. Oh, yes, this does also answer the question of why page table entries are 32 bits. They store other stuff, 20 bits and then more. Okay, so our interlude, handling exceptions, right? Things like page faults. What is the operating system doing here, right? This is gonna remain relevant for us because we're gonna find that there are a lot of times when we want the operating system to sort of kick in and handle something for us. Right? So let's just think about what this is like. We're going to write some very short pseudocode, right? What has to happen here? All right, so first of all, we talk about exceptions. We typically talk about the operating system's kernel managing exceptions such as page faults. So you can think of the kernel as the core of an operating system. If you have heard kernel, the word kernel spelled this way in other contexts, this makes sense. Okay, a kernel is often like the core of something. Like in math, you'll sometimes talk about kernels. In vegetables, like a kernel of corn, right? It's like the important part of the corn. All right, same thing. This is the important part of the operating system. All right, it's going to do all sorts of important stuff. We're going to talk a lot more about it. So when it handles an exception, what's going to do? What's going to happen? All right, well, we want to switch into kernel mode. Right, we want to be the kernel and say, okay, the operating system kernel is on now. It is handling this problem. To differentiate from kernel mode, the opposite we talk about is user mode. Right, so you get user mode, kernel mode. I haven't used those terms yet because you haven't needed them yet, but you need them now. So we've got to switch from one mode to the other, handle the exception, and then switch back. All right. I've given you 3 lines of pseudocode. We're only going to end up with 3 lines of code. We're going to do this at a very high level. Right, but I want you to understand what's going on here because it really matters. So first of all, the way to get from user mode to kernel mode and back, there is just a bit in the processor that says whether we are in user mode or kernel mode, right? The UK bit, user kernel bit, right? That bit helps the processor control access to certain kernel specific actions. And in fact, this is gonna maybe feel like kind of a self-referential definition. The code that runs in kernel mode, that's the kernel of the operating system, right? That is how we define it. So I'm gonna, switch this user kernel bit over to K, handle an exception, switch it back to U. All right, again, super high level pseudocode here. That's all we need for this lecture. Calling the handler for a particular exception, there's a table there. One way to do it, there's a table of handlers, just call the right one, right? Each handler would be totally different. For instance, the page fault handler would take care of bringing the requested page into memory, perhaps ejecting a page from memory, putting it onto disk if we're really running out of room, right? This idea, and again, I know that you might look at this code and think, this is so small, like what? 2 of these lines look very similar, This idea though, getting the kernel to kick in and take over and do something has a ton of relevance, right? It's gonna happen over and over and over. So I want you to have just a sense of like what actually happens, okay? This ends our brief interlude into handling exceptions, which means we're back to rectangles. All right, so we've talked about this, all right? There's a bit in page table entries, pages in a memory, throw an exception, kernel kicks in, gets it into memory, all right? Now, still haven't answered the question of, does this really do what we wanted to do? As long as we're here, though, one piece of functionality that you have encountered before in life, there's some parts of memory that I might want to, I'm fine with a program reading to, but I don't want them to write to, right? How will we do that, right? How does the computer implement this, right? You can imagine, for instance, again, even though I've set up in this particular example, instructions and data for program 1 being totally separate from instructions and data for program 2, imagine that they both need to read a shared library or a shared database or something like that, but we don't want them to write to it, right? This is entirely possible, solved in a very similar way to how we dealt with pages in memory versus in disk, right? The last bit, the pink bit here, just the present bit, right? P. It's conceivable that we want, say, program 1 to be able to read data but not modify it. There's another bit, right? The read write bit. Is a program allowed to write to this address? If it tries to write to it and it's not allowed, we get an exception and the kernel steps in and handles that, right? So you can see where this idea of handling exceptions, it's coming up over and over again, right? A program has done something that we don't want it to do, the kernel kicks in and deals with it, right? Now, I've only given you 2 examples, although I did, I compared the kernel to corn, so you should know it's very important, right? It's this very important part of the operating system. It would be bad if something happened to the kernel, right? It would be bad if programs tried to, overwrite stuff that the kernel was in with, or even in some cases tried to read it. That could allow them to do all sorts of bad things, right? So how do we deal with this, right? What happens if a program tries to access some part of memory that only the kernel should have any access to, right? We really, really, really want to protect this kernel. In fact, the kernel is just as interested in enforcing modularity between itself and user programs as between user programs. And in fact, perhaps even more so, right? Well, this is coming up here because again, there's a bit that helps with this, right? So you've got a present bit, you got a read write bit, and then now user supervisor bit. Is the program allowed to access this address at all, right? Or is this a physical address that is only allowed for the kernel? If not, we get an exception and the kernel handles the exception, right? Now, this is the place where we can finally think about, well, does this really work, right? Does this help us, right? This last piece, without something like this, a determined program could still try to attempt to circumvent some of the modularity we're trying to enforce here. It could try to do clever things like modifying page table registers, right? Or, kind of mucking around with other stuff that is really only the kernel should have access to, and to try to overwrite instructions and data for other programs in that way, right? But this last piece lets us protect from that. If you're kind of thinking in the world of programs, like you might be thinking, well, if everything's really well behaved, this seems like a lot of overhead. That's maybe true, but things are not well behaved. There are bugs in programs. There are lots of bugs in programs. There are attacks and all sorts of things. I saw a question in the chat: is the address deterministic? So that's something we will talk about in May. A lot of operating systems, no, it's not. There's a lot of randomization here so that you can't just guess where things are. But if you can guess where things are, I will show you some powerful and terrible things that you can do, but not until May. We're not ready for that yet. All right. So the bits here, we have present bit, read write bit, user supervisor bit. Although I totally happy to get questions in the chat. I do not feel like you have to memorize every single exact name. You will have notes on things like exams and things like that. So present bit, read write bit, user supervisor bit. We are not going to worry about the other bits for now. We're just going to concentrate on those three. All right. So I told you there were two places we needed to go. Right. Remember, we used to have this picture. Right. The other places we want to go is performance. Right. Performance is a huge issue here. Right. It's a huge issue because this activity is happening constantly. Every time we access any piece of memory, all of this executes. All right. So what does this mean for us? To make this fast, page tables are allocated contiguously in memory. All right, it is one big block here, of 4 megabytes. I forgot to put the size, but it's 4 megabytes. All right, one big block. All right, which means that even if our program only ends up accessing like two or three rows here, so we've allocated 4 megabytes because we want this virtual page number to be a true index, like a fast index into a contiguously allocated array. We don't want to have to jump through something like a linked list. We just want to be in and done, right? So every page table is going to be 4 megabytes. That's still kind of a lot, right? It's still a lot of memory. We can do better, all right? Here's how we are going to do better. All right, we're going to use a different technique called hierarchical or multi-level page tables. So I've changed the example here. I only changed the address because I need this address to do something a little bit different. All right, so in our normal system, we would take this address, take the top 20 bits, that's an index into our page table, and we use the offset. In the world of hierarchical page tables, the memory management unit is going to get the same address, but it's going to treat it differently. right? It's in my slides, it's going to add more colors, right? Well, those purple and blue boxes shouldn't be there, but slides aren't perfect. I'll fix that in the ones that I post after this. All right, so how is this going to work? What do these colors mean? Right, what am I going to do with this? So I'll explain to you what all these colors mean. So first of all, you can see the pink, I've shaded the top 8 bits, right? These are hex digits. Each digit is 4 bits, right? This table is the only one that gets allocated initially, and the top 8 bits index into it, right? This means it has 2 to the 8th entries, so it's much smaller. It exists, it's contiguous, but it's much smaller, all right? So I take that 0, 2, it indexes into this table, right? So I would get to row 0, 1, 2, right? Now, what's going on in that row, right? Because I have not used this whole virtual address yet, right? I'm not done. This row is going to point to another table. This really is like rectangles all the way down. I didn't know this when I was making the slides. It's going to point to another table. I made it a green table, right? And then the next 8 bits of this address are going to index into that table, right? So I took 8 bits in pink, 8 bits in green. Same thing's going to happen here. I use my index. That row points to another table, right? That's an even smaller table because I used 4 bits here, right? And we'll get the physical page number from there, right? So that's how we'll end up with this physical address. Now, this looks like I have made your world much worse. I've added so many more tables, all right? Because if you expand this out, potentially for every row in a page table, like every row in the pink page table points to a different green page table, right? And every row in each of those green page tables points to a different orange page table, right? It's so many tables, right? So why is this potentially better for us, right? Oh, also, I went with 884. Again, you can use different bits, right? The reason this is better for us, if there's a row, say, in this pink table that is never accessed, right? Say that my CPU never accesses a virtual address that starts with 03. So I never get to row 3 in that table, in that pink table, which we call the second outer table. It's not a great name, right? There will be no green table allocated for that row. So in fact, if this address that you see here on the slide, if this was the only access ever made, these are the only tables you ever get. These 3 tables right here, right? They are each much smaller, right? In total, you deal with far less storage in this particular example. Now, this is not perfect, right? There are trade-offs. There are a lot more lookups in different tables, right? Like, you know, for this one address, I looked up in the pink table, then the green table, then the orange table, right? I had to look that up, right? And this also introduces more exceptions. Every time we make an access, if we arrive in a table at a row we've never accessed before, we have to basically ask the kernel to create the next level of page table, right? To allocate that for us. Because the whole problem we're trying to deal with is we don't want to pre-allocate all this memory for a page table that I might never use, right? So there are drawbacks here, right? More lookups, potentially more exceptions, which means a lot more switching between user and kernel mode. But this is sort of an interesting thing for you to think about in the context of what we did on Monday and what you did on Tuesday. You saw in DNS, which seems totally unrelated to this, DNS, we used hierarchy to address some aspects of scale, right? The hierarchical design of DNS lets us scale up to the internet, right? Combined with some other things, but this is also hierarchy applied to scale, right? The scale here issue is really with memory, not with speed, right? But we still have this idea of there being a hierarchy of tables, right? So this is a different way to deal with page tables. Right? So this is one kind of big collection of performance issues, right? The first one is just these tables have to be contiguous. That has some drawbacks. What are some options for dealing with that? All right, the second performance issue, which I will say much less about, what if we end up looking at the same piece of data over and over and over again, right? Again, these accesses are happening all the time. This is all of this lookup, even though, I think sometimes if we're more used to programming like at a high level, looking up in a table is so fast, but you're looking up in this table all the time. Can we make this faster, right? And what are the techniques that we have to make these types of things faster? Caching. All right, so you've seen caching in 004. In theory, it exists to make common lookups faster, right? Put something that you are referencing a lot in, sort of the easiest place for you to access. You've also seen it in the context of DNS, which again, these two systems feel really, really different. But you can start to think about caching as a more general technique and think about like, well, okay, how do we know if it's working well, right? We look at the hit rate, how often I ask for something and it's actually in the cache, right? But what else do we have to worry about? We have to worry about how we decide what goes in the cache, right? We have to worry about how we deal with consistency issues, right? If I've cached a piece of data in some particular part of memory, or even in a particular part of the memory management unit, and then it changes on disk, how do I get that update propagated correctly? How do I keep things consistent? You saw the DNS kind of says like, oh, eventually it'll be okay. And that works, right? We design around that. It doesn't quite work here. I told you all that when I learned this stuff, I really hated page tables. I specifically hated worrying about how to keep caches consistent, but now I like it very much. So growth, right? All right, so this is not a performance issue that we're going to get into a ton in lecture, but I want you to start thinking about these things more generally. All right, so we have 2 minutes left, which is perfect. This is where you landed today, right? So we've talked about virtual memory. My hope is that, I know this is an intense lecture, especially compared to the first 2 lectures in this class. You probably will need to review it. That's fine. My hope is, though, not just that you understand how virtual memory works, like how that lookup is done, but that you understand why it exists, right? And one thing I want to say to you, which you will talk way more about in recitation tomorrow, some things aren't easy to virtualize, right? Reading and writing to the disk is not easy to virtualize. Dealing with network links, those aren't easy to virtualize, right? And yet we still write programs that read and write to disks, open and close network sockets and things like this, right? For those, your operating system presents abstractions to you, right? The reason I'm introducing this to you is because you'll start talking about Unix tomorrow in recitation. And choosing the abstractions to present to the users, to programs, that's a big part of how we design operating systems. All right, so just to close out here, I don't know why these are animated. Here are some things you have seen today. All right, and then I'm going to do one last poll, still anonymous. All right, let's see. Oh, okay. I just want to see how you're feeling about things now at the end of this lecture. Okay, totally anonymous. We are not like, that's totally fine. And I will look at this question, which I think Nick has already answered. Yes. So each of the tables are allocated contiguously, but they do not all necessarily need to be contiguous across the tables. So like I might have pink table contiguously here, green table contiguously here, orange table contiguously here, rather than having them all in a row. So yeah, okay, I'm gonna let this poll go for a little bit more just to see what the results are. But I will stop sharing so that I can see all of you, and I will stop recording.